MSU-FCU is proud to partner with MSU Alumni Association to bring to you a variety of programs and events across the campus. In particular, we're very pleased to support Coffee with the Profs. I thought I would take a moment and share with you the history of the credit union. In 1937, the credit union was formed by faculty and staff on campus. Those individuals came together to create the credit union because they were not able to be banked after the Depression. And for the first 20 years of our organization, that volunteer board of directors managed the credit union. And if someone needed a $100 loan, they would call 10 members and ask them for $10 in deposit. With that, in 1957, we grew large enough to hire our very first employee, and she managed the credit union for over 30 years. Today, I'm proud to say that we are the 46th largest credit union in the United States with $4.2 billion in assets, 865 employees, and 265,000 members worldwide, many Spartan alums, faculty, staff.
From Michigan. Prior to his appointment at MSU, Andresen held positions with the National Weather Service and with the USDA's World Agricultural Outlook Board in Washington, D.C. He has a BS in meteorology from Northern Illinois University and an MS and PhD in agricultural climatology from Purdue University. Andresen currently serves as the director of Michigan's EnviroWeather Information System, which supports weather-related decision-making across the state, as co-director of the Great Lakes Regional Science Assessment Center, and as an extension specialist maintaining an active outreach program, including dissemination of weather and climate data and related information to the general public and continuing education activities. The primary focus of Andresen's research has been the influence of weather and climate on agriculture, both in the United States and in international production areas. Please join me in welcoming Dr. Andresen.
Thank you very much, Liz. Am I hooked up? I'm live? Very good. That's a good start. It's a pleasure actually to be here. And so thank you for spending your Monday morning with coffee, and I have one as well here. So, but I'd like to spend the next hour in a discussion about climate, as Liz has introduced. And I'll grab. I noticed a little bit of an extra spring in people's step today, with both because of Saturday night and the game, but also it's sunny today, and it always changes people's disposition. So I'm as your speaker, I'm very, very happy about that, and fewer grimaces out there. I've got several different pieces of what I'd like to discuss with you here today, but I guess to start off with, it's important to note that there are links. It's a story with many, many interlocking pieces, and I'll try and identify those for you. So again, even though we're going to be talking about history and we're going to be looking ahead and climate models and so forth, there is an interlocking thread, or more than one here. I want to start though with, and this is in her introduction, Liz has already talked about this and some of what she said about what I do. The words weather and climate were used more than once. And so I think it's important to talk about this and setting the stage for what we are going to talk about. And these two words, these two terms are very closely related. They both refer to variables that in our environmental variables that we observe, monitor, measure, but the issue is one of time. Meteorology and weather describe these processes in very short time frames. So hours, days, seconds. Climate, on the other hand, same thing, but now we're looking at much longer time frames, typically decades, centuries, millennia, and longer. So, and there's a really, really interesting quote. This is typically attributed to Mark Twain, but as is the case with many things, there's some evidence that it was perhaps his publicist that actually came up with this. And and Mr. Twain borrowed that and put his name on it. But it perfectly describes this. Climate's what we expect, but weather's what we get. And so one of the ideas here is that weather really is a part of climate, just in the short term. And so we are going to talk a lot about weather, especially weather extremes, but they are a part of longer-term climate. And these changes over long periods of time is really some of the focus of what we're going to talk about this afternoon. So let's start with some introduction. One other theme, one other take-home message here, definitely. One thing, there's a lot that is less than certain, a lot that's less than certain, and is not known. One thing we do know, without any question though, is that climate, one word that you should associate with climate is dynamic. Climate changes. Our world's climate has changed from the beginning. It's changing now. It will change in the future, even without people. And I'm going to talk a little bit about that relationship here in a second. And this is maybe the smallest print that you'll see, so I apologize for this. But there's a lot here. There's a lot of story to tell. And if I can, starting from 400 million years ago with tropical conditions here in Michigan. And if you're real close up here in the front seats, front row seats here, you can see our state, I think it's our state stone, yes. The Petoskey. And what is Petoskey? It's fossilized coral. And so many times when if I talk with students or young students and so forth, and everybody who's grown up here, I didn't grow up in Michigan, but certainly with my family, we spent many hours combing the beaches and in northwestern Lower Michigan on Lake Michigan, looking for Petoskey. And it's a rite of passage for people here. But what is that? And that coral, and you ask the student, do you find anything unusual about that? And usually one or two students will say, well, isn't coral something that's associated with tropical conditions? And of course the answer is yes. It is a fossilized coral, and it reflects conditions, tropical conditions, again, that long ago. Now, contrast that right below it to the Wisconsin glacial period, our last major glacial period, when this area where we're sitting was covered by, well, depending on what year, probably a mile thick sheet of ice. And there's been everything in between. You can see some of the pieces here. After the end of the Wisconsin era, the end of the Pleistocene, about 12,000 years ago, climate actually warmed very rapidly in our part of the world. And this is done, you might ask, well, who was out there to hold a thermometer or an instrument? Well, of course, nobody at that time frame. But we look at this through sediment cores, pollen counts. There's a number of ways, something called paleoclimatology. And there are scientists that specialize in this and can tell us an awful lot about what happened, even though we did not have instruments. I'm going to talk about instrumental record too. But it's interesting to note that there have been major changes just in the last 10 to 12,000 years. The climate that we have now, currently in the upper Midwest, the Great Lakes region, basically the last several thousand years. And the vegetation reflects that. But earlier than that, again, following a glacial epoch, we actually had xeric species with dry climate and cacti and other dry-loving types of plant species. There's been an incredible amount of changes. And again, we'll look, this is just the historical part of it, but again, climate is dynamic, it is changing, and you might say, well, why does climate change? Well, there are a number of issues here physically. One is that the large plates that the Earth's crust make up the Earth's crust here are not stable. They're moving as well. And when we look at that Devonian tropical era that we had several hundred million years ago, the plate that Michigan and much of North America is on was closer to the equator than it is now. And of course, there's more energy coming in from the sun. The energy from the sun drives all of our weather and climate system. And that's another thing. There's a little bit that comes from other sources, some of it internally from geothermal, but it's a tiny, tiny, tiny fraction of what comes in from the sun. And essentially our weather and climate, and something you learn as an undergraduate student in atmospheric sciences, that the imbalance in heating between the low latitudes of the Earth and the high latitudes, you build a difference in energy, and energy flows downhill. It's the way the physical world works. And then energy flowing downhill along with the rotation of the Earth once every 24 hours on its axis. This is the majority of it explains most of our weather and climate. Now, of course, there's little micro variations in that, but that's in essence what sets the system going. But that differential heating is always been there. It always will. And again, some of it's due to the fact that the Earth, the orientation of continents is not always the same. We have sunspots. Everybody's heard about those. Those are typically, though, not as large a factor as the tectonics. It's a very, very small variation in the output of the sun. Remember, we talked about all that energy coming in, streaming in from the sun as a result of thermonuclear fusion on the sun's surface. There's a little bit, but it's not enough to account for many of the major changes in climate. But there's a little bit. The big one here, I think, and this is one you might not have heard about, but it is the primary one describing most of the major changes, especially in our part of the world. It's something referred to collectively as the Milankovitch theory. It's named after a naturalized, he's a Serbian-born mathematician who worked in the early part of last century. And he really is one of these stories about somebody you feel bad for. He had a number of personal tragedies and worked through and just had a really difficult life, but was very, very bright and innovative and realized that probably small but still measurable changes in the Earth's orbit around the sun, including things like how long it takes to get around its orbit of the sun, the Earth at the 23.5 degree tilt. Well, it turns out that that's not exactly 23.5 degrees all the time. There's a little bit of a wobble. But several of these, and imperfections is probably too strong a word, but subtle differences once in a while could constructively interfere to cause a change of a couple percent in the amount of energy coming into the Earth system. And that, again, that climate system, what's driving it. And this is the primary reason for the glacial interglacial cycles of the last, well, many, many millennia, something called Milankovitch. And unfortunately, Milankovitch passed away before he was sort of vindicated and proven right. He worked back in the 20s and 30s, and the theory really, after more data and more information was available, by the 50s and 60s, the climate science community realized that he had been right. His theories had been right. Now, we have a couple of other major impact type of, literally, figuratively, large volcanic eruptions, and we'd almost have to refer to these really as super volcanic eruptions. The vast majority of volcanic eruptions do not cause changes, certainly in climate, other than maybe very, very local to where that eruption takes place. One of the last super eruptions we had was Mount Pinatubo in the Philippines back in the early 90s. And the issue here, of course, is that with this large explosion of volcanic material, dust and ash, it needs to get to the second layer of the Earth's atmosphere, the stratosphere. The lowest layer, the troposphere, about 10 miles thick, where all of our weather occurs. If that volcanic material is released into that area, it typically settles out by gravity or is scavenged out by precipitation. So it usually lasts there only a few days or maybe a few weeks. If it can get to the second layer of the atmosphere, it could stay there for long periods of time. But fortunately, only the very strongest eruptions do that. Mount Pinatubo did that, and the ash and dust from that eruption stayed up more than a year and a half, and global temperatures cooled. And the issue is, of course, with this fine 1 micron size, typically, dust and ash particles, some of which are acidic because of sulfur. So you have sulfur dioxide and sulfate particles, which turn to small droplets of sulfuric acid when they combine with moisture in the atmosphere. They turn out they're highly reflective. And so these large dust clouds, which eventually encircle the Earth, as they did in Pinatubo's case, they block out a few percent of that incoming solar radiation. So just like we saw for tectonics or variations in Earth orbit, it's about the energy coming in and going out. And but only the strongest volcanoes can do this. Similarly, and this is probably the most interesting one. Once in a while, we'll get a large meteor to make impact, and because of the release of energy when this thing hits the Earth's surface, if it stays intact, you can do the same thing as a volcano does and release a huge, huge dust and ash field. The most significant and famous one, you may have heard of this, is a meteor impact about 65 million years ago in the Yucatan Peninsula in Central America near the village of Chicxulub. And it was a meteor which was thought to be probably at least 1 kilometer in diameter. But it released huge, huge amounts of energy with a huge dust and ash fill that's encircled the planet and caused a dramatic and rapid climate change. This is sometimes called the KT extinction discontinuity, where we lost a significant fraction of the species, and many of them were dinosaurs on the Earth at that time, and that's the primary theory behind that. Probably, and again, this is still not conclusively proven, but it's highly likely that that's what happened. Finally, something that's more subtle, but is going to play a role in something else we're going to talk about, and that is that periodic changes in the Earth's own budgets of carbon and nitrogen especially cause changes in climate. How much is in the Earth's crust? How much is in the biosphere? How much is in the atmosphere? Big issue. Big issue, and it changes. It changes naturally over time. But it also turns out that humans are interfering or changing the rates at which some of this happens. So again, these are completely natural parts of our system. They always have been. They always will be. Now, there are also human factors here. I've just talked about greenhouse gas concentrations, or at least started to introduce that. And that's the idea that because the Earth has an atmosphere, it's many, many degrees warmer than it would be otherwise. Well, we would not have life on the Earth otherwise. And the issue here is that with these so-called greenhouse gases, and this is review for, I'm sure, for everybody here, but the issue is that the shortwave, high-energy solar radiation coming into the system can pass relatively easily through these gases, but when the Earth tries to re-emit some of the energy that it absorbed back to space, which is the natural scheme of things, again, we don't build surpluses or deficits of energy in natural systems, but when the Earth re-releases that, it's in a longer wavelength, and it turns out that some of these gases block some of that. In essence, it's like putting on a blanket. And why do we use blankets? Well, it's because the blanket interferes with some of the heat loss from our body and keeps us warmer. Same thing is true for the atmosphere. Again, the atmosphere, the Earth is much, much warmer because of the atmosphere. And as we know, this is changing. This is changing, and I'll come back to that in a second. There are some other trace gases in the atmosphere, like ozone, that are somewhat complex, but also play a role here in terms of changing the climate, and one that you might not have thought about: land use change related to human activity. It could also be natural, but a lot of this is human. I'm going to give you a couple examples of that. If you change a landscape over a large enough area, it turns out that you can change at least the local and sometimes the regional climate as well. So that's another factor. And finally, just to carry back to the greenhouse gas discussions, this is a graphic showing primary greenhouse gases in the atmosphere from the middle of last century, 1950, up to, well, this is dated now. This is from one of the Intergovernmental Panel on Climate Change releases, going out for a projection out through the middle of this century that highlights or shows the growth in greenhouse gases. The big ones here, of course, carbon dioxide, methane, nitrous oxides, and then you've got a whole host of other trace gases. The three big ones, though, are these three here, especially carbon dioxide. Probably at least about 60% of that warming effect is from water vapor is one too, by the way, but that doesn't change the way that these gases do. I'm going to come back to that, but what you can see here is a gradual increase in the concentrations of these gases. These are projections of these gas concentrations into the future, and of course the concern is that as these increase, we know from both from the physical theory, we also know from empirical observations that there is a very, very strong correlation between the concentrations of greenhouse gases like carbon dioxide and temperature over periods of time. This is really small, but this is a graphic that goes back about 150,000 years. It's using ice cores from Antarctica. And what you can see here, both in the blue are carbon dioxide gas concentrations. The yellow is the surface temperature. It was done, again, with some of the paleoclimate techniques. And here's where we've been. This one's a little bit like Hebrew. It goes backwards from right to left. And then here we are at the current. This is the recent uptick in carbon dioxide concentrations here over the last, since the beginning of the Industrial Revolution. And then this is projected out in the future. We just passed 400 parts per million in terms of carbon dioxide the last year or so. And depending on what one assumes about the future and economic development and growth and renewable energy, there's a number of issues here, somewhere between 500 and 700 parts per million possibly by the end of this century. Now, it's also important to note at this point in time that this is, we don't know concentrations going way, way back in the Earth's long-term geologic history, but this is one issue is here. Even though these levels have probably been attained before, the issue is that they rarely have had an increase this quick, this fast. So it's the rate of release into the atmosphere that is one of the biggest concerns, and I'll address that in just a little bit. In terms of carbon, it's not some kind of foreign substance. The only one of those gases, chlorofluorocarbons, halocarbons, those are man-made compounds. They do cause problems, but most of these greenhouse gases are all natural substances like methane and nitrous oxides. But it's interesting to note here, and this gets back to this point of what setting the stage right now, where we are and where we've been recently. If we look at the carbon budget of the Earth, carbon's a very, very common substance in our Earth's crust. We also have carbon in the atmosphere, carbon dioxide, the gaseous form of this. And ultimately, it turns out the vast majority of carbon in the Earth's crust is stored in ocean sediments, calcium carbonate with sea creatures that create shells and so forth and then fall to the bottom. That's where the vast majority is. There's also another large piece of this fossilized carbon as petroleum product. Coal and natural gas, those are all fossilized forms of carbon. They were in the atmosphere at one time. Plants absorbed that as part of photosynthesis, and ultimately when they died and so forth, they were incorporated into the Earth's crust and kept stable for a long, long period of time. So the vast majority of carbon is in that form. The problem is that by using these carbon fuels, especially fossil fuels, we are releasing that carbon back to the atmosphere at a relatively rapid rate. And if you look here at some of these different pieces, some of that is taken back up by plants. The oceans, phytoplankton, which use carbon dioxide basically in the part of their life cycle, they absorb some of it in the oceans. But if you do the math here and look at this, it turns out that you've got, these units here are gigatons of carbon each year. There's a growth, and we saw just this part right here. That's this atmospheric growth. The carbon that's taken out of the crust and released to the atmosphere and stays in the atmosphere. And unfortunately for carbon dioxide, it has a long half-life. Once it's released, it's at least a couple hundred years, typically 300 or 400 years in some cases. So once it's released, it stays in the atmosphere for some time. The same is true to a little bit lesser extent for methane and nitrous oxide. So that's a part of this concern about where we are now and where we're headed. And I'll come back to that. Now, let's flip back the pages and look at people. Again, this idea of climate changing over time. People had to deal with this before. This is not a new thing either. And I've got a list here. It's a long laundry list, and this is by no means exclusive. But for the last tens of thousands of years, humans have had issues with their climate. In many cases, it was a bad relationship. And one of the things you can see here, going back to Mesopotamia and the advent of really the beginning of agriculture about 10,000 years ago. Drought is a word used here many, many times. Because of the lack of moisture and water, humans could no longer grow enough food to keep moving. You can see one here, 200-year drought in Mesopotamia. Here's one that's not, a catastrophic flood in the Black Sea Basin. This is thought by some to be maybe the origins of the Great Flood story. And so it's something that actually happened. But this is also around 5,500 years ago, also was the beginning of agriculture in Europe as it warmed up after the end of the last ice age. Here's one that's important, 4,000 years BC. So 2,000 years, or 6,000 years before present, because of this threat of drought in places like the Middle East and the Tigris-Euphrates Basin in Mesopotamia, humans got their act together and were clever enough to figure out that they could store water in places and then use it when they needed it. And this is really the beginning of irrigation, which of course is a major part of our food production system now. Here's another drought with the Akkadians in the Middle East and Mesopotamia. Moving closer to here, the collapse of the Mayan civilization. This one is debated still, but drought is thought to have played a major role in that. If you've ever been down to Central America, it's a fascinating culture that's somewhat vanished, but drought played a role in that. Here's one that I was going to spend a little bit of time with, and that's just before 1000 AD, Leif Erikson and his followers, who were basically kicked out of Iceland for rabble-rousing and aberrant behavior, and sent westward, landed on the southwestern part of what's Greenland, now today Greenland, and basically had a fairly successful settlement there. They sent back ivory from seals back and forth to Iceland and back ultimately to Europe, and things went very, very well. There were actually, I think at the peak, about 25,000 of these European settlers that lived in that part of the world. Now we think of Greenland this day and age and not exactly the most hospitable climate. Well, it turned out that this coincided, at this period in time, it coincided with an abnormally warm epoch, especially in the North Atlantic, but also in Europe. The medieval warming period, and so the two were not independent or events. But by the 14th century, beginning of the 14th century, the climate there began to cool off again and be like it was in many, many previous centuries. And there's two parts of the story. Ultimately, and these settlers brought their European agricultural system with them, mostly animal protein, so forage and cattle and goats and sheep. And that's fine if you have more than a 50-day growing season during the course of the year. There's something you can feed them. But when the climate turns Arctic again or subarctic, it's a much, much more difficult issue to deal with. And the neighbors they had there, the indigenous peoples at that point in time, the Inuit that lived in, they did not get along very well, at least for the historians tell us. But even more compelling was the idea that these Inuit populations that lived in Greenland were nomadic hunter-gatherers still. And they had been there for a long time and lived in this very, very, very demanding extreme climate. But basically it was by fish and what was around them, living off the ocean, and they were able to cope with this. And the Vikings never figured out or didn't look at their neighbors, even though they didn't like them. They could have learned and maybe had adapted. So the Viking settlement in Greenland is a case example 1A of what not to do in terms of a change, of what to do in terms of a changing climate. The last piece here, what the Vikings didn't know at that time was that the climate globally was changing into a cooler period. It's referred to collectively as the Little Ice Age. And I didn't know it at the time, but when I was a little boy, my grandmother told me stories about my great-great-grandparents and where they came from. And well, it's in southern Sweden. And there were many economic issues, of course, like many people. And this is probably true, I'm sure shared with some of you as well in your own family histories. But one of the major reasons they came here was crop failure. And they had frosts and freezes during the middle of the growing season, and they were starving. They were hungry and had no money to buy food. So one of the reasons they left Northern Europe and came, ironically, to a climate which is colder than what they left. They didn't know that at the time, but it was certainly a better place for agriculture. That was the end of the Little Ice Age. So there's always been this cause and effect with climate and people and migrations of people. It's happening now. We have a flux exodus of people from places like Africa, the parts of Northern Africa and the Middle East, leaving elsewhere because there's a lot of political issues, but there also are climatic issues. Desertification is a big one. So this is not a new idea, and it's something we have to think about as we look ahead. So some human history there. Let's look at the actual climatic record, and I'll I'll try and pick up the pace here a little bit. But we have roughly about 150 years of reliable records from instruments, thermometers, rain gauges, enough to tell its story. And so I'm going to show you here, there are many, many graphs you're going to look at, but I think they do tell a story. I'm going to start with the best temperature records we have, both combined over the land and ocean surfaces of the world. This record goes back to 1880, and it goes up through, officially the graph goes through 17. I've added 2018. We just got the data from last year here that have been made available. Each of these bars represents the difference in the observed global average temperature, again, with all those stations averaged together, minus a long-term average from 1901 through 2000. So the 100-year average. And so the blue colors here, the blue bars, that's when that individual year was cooler than that long-term average, and then the reds are opposite. And what you can see clearly since the beginning of last century is a distinct warming trend that's taken place. It's a little bit less than 2 degrees Celsius, or a little bit less than 2 degrees Fahrenheit. It's more than 1 degree Celsius. We have had above normal, relative to the long-term mean, global temperatures for 42 consecutive years. That's one. When you add 2018, turns out is likely going to be, we don't have the final version of the data, probably the fourth warmest year on record. The warmest year on record, you can see here, occurred in 2016, but all 4 of the warmest years globally have occurred in the last 4 years. That's another thing. It's an unmistakable upward trend that's taking place here. So the world, we could have maybe 15 years ago, 20 years ago, we could have probably debated whether the Earth really is truly warming. There really is no more debate about this. The world is getting warmer. There's all sorts of other evidence, melting ice, warming water temperatures. All of these things collectively are associated with this global trend. Now, the other important thing to note is that not all areas of the world, this is the average. So there are some differences around the world. This is for the state of Michigan, and very, very typical of the upper Midwest and the Great Lakes region. This particular series begins in 1895 and goes up through the end of last year. Michigan is also warmer, but not quite to the same degree. You can see here at the beginning of last century, there was a sideways trend in temperature. There was some warming in the late teens up through the 20s and 1930s. That was followed by a little bit even of a cooling trend during the 40s, 50s, 60s, and 70s. And then beginning at about 1980, this is interesting, we've had about a 2 degree Fahrenheit warming on average that's occurred. Now, one important thing about this is, so overall we've warmed about a degree and a half on average since the beginning of last century. It turns out that all of our seasons are getting a little bit warmer, but some more than others. And one that is warming relative, and there's also a caveat on this, but the winter season and nighttime temperatures are some of where we see the largest changes in taking place. These are December, January, February mean temperatures for Michigan for the same time frame. And the blue line here shows the long-term trend, the green moving average. That's actually, if you're looking at these, that's what this red line here is, the 9-year moving average. And it gives us roughly the decadal types of changes in these variables. And you can see some of the same thing happening here. This is especially true over northern parts of our region, the UP, northern Wisconsin, northern Minnesota. Some places we've seen as much as 6 or 7 degrees warming just in the last 40 years. That's a big change. Big change. There is, the caveat here is we haven't been exactly having the warmest late winter since the beginning week of January. We did in December and up to the first week in January, but since then we've turned cold. We also had some extreme winters back 2013-14, 2014-15 back-to-back. Those were the 2 coldest back-to-back winters since 1921 in Michigan. It's been a long, long time. So there have been a couple of winters here recently that making us think a little bit, maybe at least of a temporary leveling off of this pattern. So it's important to note that. And well, this winter we've had certainly, it's going to end up colder than average. Not anywhere like what we saw in 2013-14, but it's still going to add up to be colder than normal. Because here's one of those interlocking pieces. if we look at long-term, this is the amount of ice cover collectively over the Great Lakes taken from satellite. This one only goes back to 1980 to 81 because of the satellite record is shorter. And it goes through 2016-17. It's from Environment Canada, and I'm hoping to get an update for this one. But the long-term trend in both the amount of ice and the duration of ice cover on the Great Lakes is declining. But here's 2013-14. You can see they jump up. That's the largest one on. And we had, probably most of you aware, we had a lot of ice on the lakes this year as well. It just, the timing of the cold weather was all together collectively. That plays a role. There's 14-15. That was followed by 2 very, very mild winters. Now, one of the things I think is also very, very important to note, and I'm going to come to this just in another couple minutes, but that is one of the concerns is that we may see now a bit of a leveling off in the long-term trend, but what has increased without question, the variability year to year. And it's one thing to say that we have some kind of a long-term tendency towards warmer or cooler or wetter, whatever the case may be, but it's a completely different one when we have these huge swings. In terms of the impacts, that's a game changer. And so we are seeing evidence for an increase in the variability, and if you're in Great Lakes shipping, or there's a number of other industries that are dependent upon it, this is a major concern right now for them. Seasons have changed. This is a mess here. This actually is from a friend of mine who put this together, but bear with me. There are 3 different series on this. This also goes back to 1895, and it goes up. This is somewhat dated. It's about 10 years old. But these are, in green here, the changes in the date of the last freezing temperatures of the spring. And in blue, we have the changes in the dates of the first freezing temperatures of the fall. And then in between the two, you've got your frost-free growing season. And this is for the Great Lakes region, 6-state region here. And what you can see is that there's a lot of variability, and then it sort of tempers off here right in the middle of this section. But then and again, about 1980, last freeze of the spring gets earlier by a week. First freeze of the fall gets later. And so what we've added here with this warmer temperature is about a week and a half of frost-free growing season we didn't have just 40 years ago. That's real. Doesn't mean it every year, but on average, that's what's now taking place. We've looked at this in Michigan, and it's not symmetrical. There's been more change in the spring season than there has in the fall. The warm-up in the spring is occurring progressively earlier and earlier with time. And before we started here, Liz and I were talking about impacts. One of the ones I work on with agriculture is this change. And if you grow fruit, if you have a perennial crop, even annual crops that are out there dormant during the winter and then respond to their environment, and as soon as it warms up, they begin to grow again. The problem is that once these overwintering crops or species, it could be natural vegetation as well, responding to their environment, once they begin to develop, their resilience to frost and freezing temperatures drops dramatically. And this is definitely true. Here we're looking at tart cherries. Michigan, of course, is the leader in the nation. It has been for some time. Fruit's been grown commercially in Michigan, tree fruit in the western part of the state for over 150 years. And they do very, very well at it. The problem is that as these seasonal changes take place, we're now looking at the date each year in northwestern lower Michigan at which tart cherries reach the so-called side green stage. You can see the little buds begin here, the bud burst. And it turns out that tart cherries, when they're fully dormant, they can take a lot of abuse, minus 30, minus 35 Fahrenheit, if they're fully dormant. But once they begin that development, now, once we get to this stage, we're talking about damage thresholds up in the low or mid-20s. Big, big change. And so if you do have the cold outbreaks in the spring, and unfortunately we still do, what happens? Well, you damage the buds, and if you damage the buds, there's no fruit, there's no crop, there's no income. Big, big problem. And what you can see happening over time here is a gradual, this is the day of the year, day 1 is January 1st. So day 121 would be the beginning of May, end of April, beginning of May. And you can see that we've actually, this event is occurring now at least a week and a half earlier on average than it did just 4 or 5 decades ago. But we still have the freezing temperatures. That's 2012. Some of you remember our heat wave in March of that year, unprecedented. In March 2012, and this is one the fruit growers don't even, the industry doesn't even like to talk about this, but in that particular year we had the warmest March on record. It's a sort of an exclamation point on this trend that we're talking about. All of these crops came out of dormancy at least a month early. And then at the end of March, of course, and for April, our climate went back to what it normally is. And we had many, many freezing temperatures. In some cases, 15 to 20 nights with freezing. It completely destroyed the fruit crop. There was, in most parts of Michigan, there were no fruit, no cherries, no apples, no peaches, no blueberries. Depending on who you talk to, at least $500 million in losses when you look at the supply chain. And agriculture, by many measures, is the second most important industry in our state. It was a huge loss. And all because, again, of this incredible 3-week heat wave during the month of June, or during the month of May, which was unprecedented. So perhaps the largest change, or the most significant change, though, historically we have in Michigan is precipitation. So we talked about warmer temperatures. It's also getting wetter in Michigan. I think most people probably would have guessed that one right off the bat. But as we look at the long-term trend, again going back to 1895 through last December, the driest decade, the driest area epoch here in our climate record back in the 1930s, the Dust Bowl era. That's true here. It's true for much of central North America, actually. But ever since the end of the 30s, by and large, we've gotten wetter and wetter. We now have 10 to 15% more water. That's both rainfall plus melted frozen precipitation as well than we did just a half a century ago. That equates to, depending on location, somewhere on the order of 3 or 4 inches of additional water. What's our normal rainfall for a month like July or August? It's about 3.5 inches. So one way you can look at this, and this is for agriculture, this is a huge deal, because we now have, on average, an extra month of precipitation bonus that we didn't have before. And if you're a plant, one of the struggles during the warm season is when you're using all the water is don't run out of water. That's the major, in terms of food production, that is the chief limitation. For the tree fruit, of course, it's these spring freezes. But for most other food crops, it's the lack or the surplus of water. And the fact that we have more of it in the system now is a very, very positive thing. We've done a lot of research on this, and there's no question that some of the increase in our agricultural production, not just here in Michigan, but also across the Midwest, is due to this wetter climate. There's less stress, less time, less duration. Doesn't mean we don't have drought stress, we still do, but it's less frequent than it has been in the past. So that's an important one. And it's also important to note here that this trend is still, this shows no signs of leveling off. It's still going up. How can you have more annual precipitation? Well, you can have more wet days. That's happening. We're now seeing something on the order of, in some cases, 20 to 30% more days with measurable precipitation now than we did 50 years ago. We're also seeing more precipitation per event. These red circles here are the changes statistically. If you take the 10 largest daily precipitation events each year, sum those up, what's happening to that sum over time? It's increasing. So the extreme events are also increasing as well. And matter of fact, this is, I think in terms of economic impact, that might be the most significant climatic trend that we're dealing with here in Michigan, these extreme precipitation events. We've seen a lot of evidence of that recently. Here's one which I'll throw out to you. This is snowfall for the 1961 to 1990 period for the Great Lakes region. Here's the same thing except a few decades later, 1981 to 2010. This is our current 30-year normals period that we're using, and it's all color-coded the same way. Can you see any changes here? There's been changes in seasonal snowfall. There's 2 of note here that you can, if you look really close, can anybody see? That's definitely one of them. I'll get back. And the other one's a little more subtle, a little more difficult to see. Look to our south in the Ohio Valley. If you look, you can see that snowfall between, again, the 61 to 90 period to the most recent period, that there's been a decrease in snowfall in areas to our south. This has to do with where our snow comes from. Most here in the Ohio Valley and in areas to our west, across the lakes, most of the snowfall here is synoptic low-pressure systems. But the issue here is that with warming winter temperatures, which we've seen, this is another link to the other things we've seen, that we're getting more precipitation, but more of it's falling in liquid form than solid form. And some of that's true even into parts of southern lower Michigan. So you mentioned too the UP, what's going on here? We're seeing increases in seasonal snowfall totals. in places like the Keweenaw Peninsula, in places like the northwestern lower. Who knows what that is? It's some of the synoptics, some of the increase in precipitation is probably contributing to this, but what happens in places like the Keweenaw Peninsula and Grand Marais, it's lake effect, snowfall. Here's an interesting one. So if you're thinking about what we said, well, hey, wait a minute, you said that the winters are getting milder. What do we have to have for lake effect snowfall? Well, you've got to have, of course, the open water of the lakes. You've got to have Arctic air masses or polar air masses move across that. We've seen several instances of that even here locally in the past several weeks. So if it's getting warmer, why are we getting more lake effect snowfall? Anybody know the answer to that? It was back there.
No ice on them.
Exactly. The reason is because it's milder. We have less ice on the lakes on average. And so the water's warmer. There's less energy required to vaporize water. So we're getting, at least for now, we still have polar air masses moving across. We're getting more lake effect snowfall. And this is also true in the lower lakes as well. So those two trends are sort of combating one another. We're seeing a little bit of a decrease here in the south, but increases in other parts of the state. But once again, like we saw for lake effect, the issue is variability. And even in these areas, like the northern upper peninsula and the snow belt areas, even though we have more snowfall, the number of days with snowfall on the ground is decreasing because it's melting more quickly. Again, back to those winter temperatures. And if you're in the winter recreation industry, which of course is number one, snowmobiling up in the UP and outdoor winter sports and so forth, the variability is increasing with time. That's bad. That's definitely not a positive trend and something of concern. But that's also, again, part of this change. Not only the changes in means, but we need to look at that variability as well. All right, speaking of variability, and I've introduced this already, won't say too much about this, but there's some interesting pieces of this, and I'll have to move quickly if we're going to get to the future here. But we know humans in general, humans have been pretty good about changing and adapting what they do to cope with these stable changes in climate. But if you change the variability, again, you go from a very warm to a very cold and back and forth, it's much, much more difficult to engineer a solution to that or come up with options to that. And that's what the point of this is. We'll dust off your history or your statistics background here. But one of the ways and engineers do this, we do this in atmospheric science as well. One of the best ways of looking at changes in environmental variables is looking at so-called distributions of these variables, whether it be air temperature or seasonal precipitation or wind speeds, and we look at the frequency of those distributions. Of course, we know they don't all line up on the same point. They differ over time. And thinking about a changing climate, again, now we're talking about many decades together, the easiest way for a climate to change in terms of this idealized, very symmetrical type of distribution. So you've got an average here, and then you've got some real cold extremes and some real warm extremes. If this were annual temperatures, for example, is you just pick the distribution up and you shift it one way, phase shift, one direction or the other. That's the simplest type of change. And in doing so, you can see here with this, if we shift it towards the right, towards warmer temperatures, you get some hotter extremes occur here. But in general, there's no change in variability in that distribution. It's only in the mean behavior which shifts upward. And I'm going to show you an example of that in just a minute. You can also change a climate by not changing the mean, but changing these tails, these extreme events, the frequency of those. That's a little bit of a scary one too. The previous climate's up here, and in your new climate, the mean is the same, but your tails are thicker. You have more both cold and warm extremes in this case. And then case 3 here, you get an increase or change in both the mean and the variance. And this is the one that is concerning because you both shift the mean up, but you've got a bunch of extra frequency of your observations here up in the tail. Many more, in this case, many more hot extremes. I'm going to show you an example of that in Michigan. Looking at the empirical data by decade from the 50s up through the first decade of this century, if we look in the United States at the frequency of record high temperature events, daily high temperatures, and daily low temperature events, you're looking here at the relative distribution of those. And what you can see with time, as the United States is warming on average, you can see that there have been many more high or warm temperature set. And what this suggests, at least if you look at this in a whole, is that we have had a little bit of that phase shift. The whole distribution is being shifted towards the warmer. That's for all of the US. If we look at events like heat waves, and that's what we have here for the Midwest, and a little dated, but for that one, we don't see much of a temporal change in heat waves. Interesting. 1930s, it's still many records, high temperature records were set in the 30s and probably will be in our lifetimes. But the point is here, no real long-term trend in the number of, these are multi-day heat waves, not individual days, but multi-day, 3-day or longer. The same is true with cold waves. Not much change, either up or down. Now, here's some data from Traverse City, which I'm using for illustration. And the dark blue distribution here is taken from 1951 to 1980. The lighter blue is our current normals period, 1981 to 2010. So what has happened collectively, in this case to mean January temperature, so this is the monthly average temperature, and you can see that the mean has shifted upward here by a few degrees, but just as importantly, look what's happened. Our tail has gotten thicker on this side. So the number of, we're still getting some of these really cold months of January, just like we did before in the last period, but there's now an introduction of some winters or some Januaries which are very mild. And this is an interesting, so both the mean and the variance here changed in this particular one. Here's another one looking now, this is the coldest temperature of each year. So the coldest daily minimum temperature each year, what does the distribution of that look like? Here's the old one, here's the new one. And in this case, the standard deviation or the variability of the shift is actually less now than it was. But you've shifted the whole thing up about 6 degrees. So our extreme low temperatures each winter on average, at least in northwestern lower, and this is not atypical for the state, they're about 6 degrees warmer than they were just 30 or 40 years ago on average. And so that's the way you can use these statistics, but it does denote a significant change, at least in our winter weather. One manifestation of that everybody I think appreciates or will appreciate, the map down here, this 1990 map, this is the plant zone hardiness from index map from USDA back in 1990. It reflects, I think the original period for that was 51 to 80. Here's the updated version from the Arbor Day Foundation, which was based on 2081 to 2010. If you look at that, they're pretty similar patterns. The map up on here and on the top, that's the relative difference between the two. And what you can see is that for almost all the entire country, except from some of the Mountain West, including Michigan, we've all gained an entire zone of plant hardiness. And that is, again, directly a result of this, because that plant zone hardiness index is based entirely on extreme minimum temperatures. So this is one solid manifestation. We don't have to worry quite as much about our plants that we're buying expensive plants at the nursery being frozen out in the winter as we did 30 or 40 years ago. That's one tangible example of how a winter climate has changed. I mentioned heavy precipitation before. I have a graduate student right now who's doing a project looking at extreme precipitation events, and the data here are compelling in terms of both more heavy precipitation. This is the 10 heaviest events per year. Reds are increases across the upper Midwest. It's also looking at the 1% heaviest events. All these, with a couple of exceptions, are generally on the increase. So the frequency and severity of heavy rain events is increasing. How much, you might say, is occurring? This table here, I've taken some extreme precipitation events. These are recurrence intervals, are the expected frequency of a 24-hour rain event at a 2, 10, 50, and 100-year recurrence interval, which means that you would expect that event to occur only once on average every 100 years or every 10 years, whatever the recurrence interval is. And this is TP40 is technical paper 40. This reflects conditions back in the middle of last century. The Huff and Angel document was done with 1948 to 1991 data. And then on the bottom here is NOAA Atlas 14, which is our current standard for heavy precipitation events. And what I want you to notice here, let's look at the 100-year event, is that this event has increased, the severity of this event, from 4.8 inches, the middle of last century now, to about 5.5 inches. So you can say, well, that's not that much, what, 15%? But it's significant when you design things like combined sewer overflows and you have to design infrastructure that will handle these extreme events. It becomes very, very important. The other problem with that is that as you design greater capacity, and that's what we're having to do right now, the costs and the expenses of that go up. That's more than linearly. It goes up. And so I deal many times with engineers and with architects that are trying to legally take this into account, and we're shooting at a moving target. Again, the bottom line is that heavy rain events, the severity and the frequency of those are increasing. And economically, I think that's our number one challenge here in terms of we have some severe weather. Once in a while we get a tornado or severe thunderstorm, wind damage. We get blizzards on occasion. We have droughts. We had a small drought last year. But economically, by and large, it's these heavy rain events. When we look at dollars, that's where we have the biggest challenge. We're most full. And that's true for most of the upper Midwest as well. That said, though, long term, if we look at drought, the occurrence of drought, even though it still happens, less severe and less frequent on average. This is an index of drought conditions in Michigan for the warm season. The orange colors here are droughts. Again, the 1930s dwarf everything else in our record. Greens are times of surplus precipitation. And you can see that the long-term trend, this is directly following our precipitation climatology. As it gets wetter, the frequency of drought and severity of drought are decreasing. Again, that's a positive thing. Well, unless you're dealing with flood control, it's a positive thing. So that's one other trend. One last thing, I mentioned land use change. This is a very, very interesting piece of very recent research, and that is based on the observation that in many parts of the upper Midwest, the Great Lakes, including Michigan, we definitely have seen an increase in precip. We talked about that. That's down pat. We've seen in some cases summer temperatures have actually cooled. This is true in places like Illinois and Iowa. Not quite as much here in Michigan, but right here in the middle. And if you remember your agricultural geography here, if we look at where's the Corn Belt, well, Michigan's on the northeastern fringe of that. This is actually looking at corn production. We've also seen another one down here, and that is the humidity in the atmosphere, not the relative, but the actual amount of water vapor in the air. That's also increasing. And that's an important one because where do we get precipitation? You have to have two things for precip. You've got to have the raw material, water vapor, and the second thing you've got to have is some way of lifting that water vapor up vertically in the atmosphere where it cools and ultimately condenses to form clouds. And if there's enough water vapor there, you get precipitation. So both of those things have to happen. But the raw material here, the amount of water vapor, is also increasing. And here's the interesting theory. The theory is that some of this is probably large-scale synoptic changes in our climate, but there's also part of this that says that we're producing an awful lot more crops like corn and soybeans, large landscapes, and those crops transpire huge amounts of water during the summer, during the warm season. 25/100ths of an inch, 3/10ths of an inch, not uncommon. And as the populations of the plant populations and the biomass out there gets larger and larger and larger with time, that's how we're getting some of the yields because we have more crops out there. It's releasing a huge amount of water vapor into the atmosphere, and some of that is showing up in our instrumental record. And that is completely consistent with, again, the increase in precipitation. So some of that's local. It's saying some of it's local water. Most of our water vapor, where does it come from? Well, the Gulf of Mexico is where most of it ultimately comes from. Some of it's from the lakes, small part, but some of it's local. And so some of this is water transpiring across the Midwest. Lower temperatures, when you evaporate water, you consume huge amounts of energy. So you get a little bit of evaporative cooling. That's also happening here. This was done with a regional climate model, a couple ways of doing this. But all these things are consistent with this, again, large-scale change in landscape. So it's not just about global large-scale factors. Some of these things are regional as well. And some of the trend that we've seen here may be related to this too. Last thing, and this is also interesting, we've touched on this a little bit. This is a graphic looking at $1 billion or greater weather disasters in the U.S. This is just the U.S. back to 1990 up through the present. And these are all inflation-adjusted numbers through 2018. And you can see a couple things. These are broken up into the different categories. The big ones here, you can see, well, tropical cyclones or hurricanes are big up there. You've got some droughts, you've got some flooding, severe storms, the green, we've had a lot of that lately. But there's an unescapable conclusion here, and that's even when they're adjusted for inflation, these things have been increasing. Now, if you're an insurance agent, this is a real concern. But even more compelling here, and this is a point of this, what we're talking, and it goes back to what we talked about at the beginning. The actual trends in some of these events. I just mentioned drought, for example. We're actually seeing fewer droughts, at least in this part of the world. We haven't really seen an increase in the number of tropical cyclones in North America. This is the US, or hurricanes. And if it's true that these events, the frequencies, are not increasing, you can make some arguments about severity both ways, but why are we seeing such a large increase? 2018, here we had $91 billion combined, at least that's the number right now that's being thrown out, with, I believe, 14 individual $1 billion plus events. Much of this was Hurricane Michael that hit the panhandle of Florida, and I'm going to end with that one. But why are we seeing such an increase in here? If the events themselves are not increasing at the same rate, who knows the answer? And it's not a good one. We as people, we have more stuff in the way. That's the issue. And so instead, we know that our climate is changing. In some cases, it's changing in a positive way. I think you could argue that warmer and wetter here in our region is not so bad. In other parts of the U.S., like the southern Great Plains, it's getting warmer and drier. That's not good. But regardless, it's changing, and our risk is changing. And instead of becoming more resilient to these, especially these extreme events, there's evidence here, at least empirical evidence, that says that we're going the opposite. And that's not good. That's not good. It's something that will have to change, obviously, with time. But throw it out for thought. And how many? Oh, keep rolling. Well, I'll try to go through. I don't have as much here. Looking ahead, how do we looked at the past. What do we know about the future? Well, the number one tool, the number one methodology that is used to try and go into the crystal ball, and I throw that's not fair. The climate science has come a long, long way in my lifetime, our lifetimes, especially over the last few decades, in understanding the interactions between the atmosphere, the oceans, the biosphere, the cryosphere, and ultimately it boils down to a set of mathematics and physics. And you're probably happy to know we could spend time with that. My students have to spend. Our discussion is conceptual, so we can add the math if you're interested. But that's ultimately what it boils down to. That's what it boils down to. And so what these so-called global climate models come up with are sets of essentially differential equations that describe the interchange between all of these different parts of the Earth's environment. Very, very difficult to do. And it really got its act together in the 60s and 70s. The first models were failures, but it was, they've come a long way. They've come a long, long way, and now do a fairly good job of replicating for current and past conditions. So if you can't do the past and current conditions, why would you trust them for the future? So the models then are initialized, given recent past data, and then said for these assumptions about the future, what happens? What does the model do? And that's essentially the game. It's not a game, but that's the exercise that we're playing. One thing about that, and there's been a lot of criticism about these models. We hear criticism about our forecast for the next 12 hours. If you can't get that right, how can you do anything for 55 years in the So I will, in defense of that, there have been quite a few studies done. This is for each continent, and this was a part of the last global assessment, Assessment 3, back in 2007, but a very important one. And it basically said for all of the communities that do these large-scale global modeling scenarios, let's all use the same data, and we'll run our models, and we'll run them out. We're going to run them for a historical period with known changes in concentrations of greenhouse gases, et cetera. And so all of these groups, I think there's about 20 different models that are in this. I don't remember the exact number around the world. It's not a cheap thing to do. But there were two, in this experiment, there were two sets of experiments run. One was running the model from 1901 through 2000 with the same greenhouse gas concentrations that you started with. And that's this blue area here. And the blue reflects all the different 20-odd models. And then this pink I don't even know what color, almost a light purple color here. Same thing, except they put in observed concentrations of greenhouse gases. And you're wondering what's the black thick line? Those are the observed changes in the same place. And what you can see is very, very good agreement, general good agreement with the increasing greenhouse gas concentrations with the observed changes in temperature. And this particular set of experiments is the source of this extremely high confidence that human activity, notably higher greenhouse gas concentrations, is responsible for at least a part, if not a majority, of the warming we've seen over the last century. And it also, just as importantly, it also gives us a great deal more confidence about what these models are doing. Again, it's the number one tool and method of looking into the future. So what do those things say collectively? Well, all of them. There are no exceptions to this. All of these models say that we will see a gradually warmer and warmer world globally. This is the global average. This is the old, this is the one from 2007. It's fairly similar, but you can see that there are a number of different scenarios here depending on what we assume about economic growth. Things like the people in lesser developed countries having access to power, improved standard of living, even things like consuming meat, which is energy and water intensive. But there are, you think the atmospheric science people argue about bad forecasts. Well, talk to the economists. They have an arguably even greater challenge. What do we assume about economic conditions, about growth, about the need for natural resources? It also says something about a change in our system. What if we were to use renewable sources of energy, or find we didn't have to use carbon? That's what this line down here, there are a number of these major scenarios, and the ones down here are, by and large, are scenarios in which we do become much more efficient in our use of energy. The one up here, this is a business as usual. This is the most aggressive warming, but you can see changes in projected global temperature here from about 1/2 degree or about 1 degree Celsius all the way up to 4 degrees Celsius. That's the global change. And it doesn't sound, so what are we talking about? Excuse me, maybe 6.5, 7 degrees Fahrenheit on average. That doesn't sound like a huge amount, but the change over that time frame, less than a century, is huge. We know geologically. The only thing that comes close to it are some of those things like meteor impacts. Very, 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 very rare in our Earth's history to see a change that fast. For Michigan, here's our best guess for the state of Michigan, including where we've been, and then depending on where we look at high greenhouse gas concentration scenarios or lower, a much wider range from about 3 degrees Fahrenheit, these are in Fahrenheit, up to more than 15 degrees. Huge, huge change. So this one was actually larger than what we had been working with in the previous generation of these, but a large, this is 2100, so this is the end of this century. Huge, huge change. What does that look like? This is something, a graphic which is oversimplified, but it puts it in a little bit different perspective. If we were to see changes of that magnitude, the climate of Michigan in the future would become more like perhaps the Ohio Valley is now, or currently has been recently, or even the Southern Great Plains with a high emission scenario. And again, this is oversimplifying something very, very complex and complicated, but it does, we all appreciate how much different climate is or has been recently in these areas than Michigan is. So it's enough to certainly think there would be major, major changes. In terms of temperature, as I mentioned, warmer everywhere, including the average temperatures, greater increase in the days above 95 degree, increasing frost-free season, we're already seeing that now, and an increase in the number of cooling degree days. Now, there's a double-edged, this one you need to say the whole story. Even though we would be paying more to cool, and I didn't have, when we first moved here in 1991, my wife and I, we did not have air conditioning, and we decided after about 10 years to get air conditioning at a decent deal, but in Michigan it was sort of an optional thing. Well, some people say, no, it's not optional anymore. We have enough days where it's uncomfortable, but at the same token, it costs a lot more economically to heat your home than it does to cool it. It turns out that's just the physics of it. So there would be some trade-off here for us as population. We would, yes, we may be paying a little bit more in the summer to cool, but our heating season we would need less. So there would be a gain there. So that's another, but all of these scenarios for the future are warmer. With warmer air, and again I'm brushing off some of your old physics here, the warmer the air is, the more water vapor it can hold. That's the pure physics of it, and it's not a linear increase, it's an exponential increase. So as the air temperature goes up, a lot more water vapor is held, and that is a part of what we're dealing with for the future. We know for a fact that it doesn't mean that there'll be water vapor there, but it could be, and precipitation, there's a lot of flags here. And overall, average precipitation in most of these scenarios, not all, but most of them suggest increases in the amount of annual precipitation, including heavy precipitation events and large, several-day totals. But the big flags here are, if you look at the seasonality of this, even though we have more annual precipitation, it turns out that the simulations, most of them suggest most of that comes in the cold season. In winter, and to a lesser extent spring, summer, when we need the water, both our natural and our agricultural vegetation needs the water. There, the projections show level or even some cases declining. So that's a bad thing. And ultimately, this is the really concerning one, and that is that we hear the statement that these projections for our part of the world suggest both more floods and more droughts. And if you look at that's crazy. It doesn't make any sense. Well, there's one physical way it can make sense, and of course, you probably know the answer. Yes, you have more overall precipitation. It falls on fewer days. So the word they don't, but they should use is erratic. Unless you sell irrigation equipment, I don't think anybody benefits from more erratic precipitation. And this is one that we're doing research on right now. It's not a good one. Erratic, more erratic. So again, longer stretches of dry weather and also wet weather as well. That doesn't do anybody really any good. So that's sort of what these projections are saying for the future. One last thing, the Great Lakes, what about those? One of our greatest treasures, natural resources, one of the largest freshwater sinks in the world. Earlier work here, a decade ago, suggested major declines in our lake levels. This is one of Catherine Hayhoe's studies. There have been recent updates, and I think they're important. This is one in between by Jim Angel, but there is work from the Great Lakes Environmental Research Lab at NOAA here recently, Brent Lofgren, Drew Grunewald, that suggests that there may be some subtle changes, but probably nowhere near. Some of them are even small increases. Some are small decreases. The jury's still out, but it's certainly not as alarming as this is. And one last thing about this, I'll cut to the end here, and that is, think about the historical trends and think about what's projected here. Did anybody notice any coincidence? A lot of these, what is projected here for the future, where have we been over the last few decades? That's it. Warmer, wetter, heavier precipitation events. That could be coincidence, but I think it's definitely, there's a flag there that we need to take into account. It gives us a little bit more confidence that those projections are somewhere in the ballpark. We won't talk about what we can do about it. Oh, I will, just to mention here. I had a couple of images here. You can either, what do you do as humans? What should the Vikings have done? What are some of these civilizations do? You can either learn to live with it, to adapt to it, or you can go even a step further, and you're going to get after the root problem and mitigation. And of course, what's needed ultimately is we're going to have to adapt to this. We are now. There's adaptation going on now, but we also have to look at the root problem. That's my 2 cents or my opinion here. We're going to have a combined strategy. But to be prepared, not like what we saw for the $1 billion insurance payouts, there are many examples of communities and organizations that basically thought ahead and tried to build some of this capacity in. And guess what? It usually pays off. This is one in a city in Minnesota that saved probably hundreds of thousands of dollars in their own combined sewer overflows. One last one, I mentioned Hurricane Michael, which hit the Gulf Coast. One of the most powerful, I think it's the third or fourth most powerful landfalling hurricane in the U.S. here this past fall. This is looking at some of the devastation in Mexico Beach, Florida, which is where just to the right of the eye wall where it made the really, really compelling story, this White House here. Notice here that this house is still here. There's 2 houses, but I'll talk about the big white one here. This is an individual who's surrounded by devastation. And the guy who built this house several years ago, he put in a couple $100,000 extra to build hurricane code, up to hurricane code, and put in special reinforcements, and his house survived. Everything else is gone. And then there's those, you can see the house. What about this guy? Well, he didn't have all this extra adaptation or all he just happened to be like the real estate adage, location, location, location. He was downwind of his neighbor who did buy. So you could call this guy the luckiest person in Mexico Beach who didn't lose his. But an example, again, there are many, many examples repeated of this. It costs a little bit extra at the beginning, but over time it probably is well worth the economic investment. So, summarize all: warmer, wetter, historical trends, that's where we've been, that's where we are right now, and in general that's what's projected for the future. This idea of variability, can't overemphasize that enough, or emphasize that enough. That's this would be a whole, next time we come, we'll talk more about some of the impacts. It's a mix. Some are beneficial, some are definitely adverse, but it's the change itself that makes things crazy. But we have to start thinking about this idea of a dynamic climate and shooting at a moving target. I think that's where we are, and I'll end. We've been through several periods or several weeks of winter. I thought it would be nice to look northern lower Michigan here, just to get some color and greenery. So, well, thanks to Lake Michigan. Thanks to the Great Lakes here. So, thank you very much.
Thank you very much, Dr.
Appreciate it.
Andresen. And I'm asking the first question. I want to know, should I be stockpiling dried cherries already?
This is, I would love to just say it's a special part of this state and this region, and there are a number of challenges for that industry, and some of them are economic, the low prices, but the weather and the climate are another. And I know that there are people who have devoted their whole lives to this, and hopefully the answer is no, we're going to continue to have that. But so it's a plug-in to use we have this wonderful industry with all this fresh food that's locally. We need to take advantage of them. Not take advantage, but certainly we need to support that industry. So hopefully yes.
Okay, and I just ask if you'll repeat the question when
my
it comes up. Thank you. Anybody else? No, geez.
Okay, we start. Yes, ma'am.
When I was a kid, they always talked about the rainforest and how they was going to affect the climate and that kind of thing, and now
Yeah.
I never hear anybody talk about rainforests at all.
Question was, we've heard many discussions in the past about rainforests and the changes and loss of rainforests, and especially in some parts of the world. We haven't heard much of that lately. What's happening currently? And I work with a graduate student who is working in the Amazon basin. And some numbers which I actually asked for twice because I didn't believe them. But she's looking at areas that have had tropical rainforests there for forever, that have recently been cleared for agriculture. Some of that is for pasture, for livestock and animals grazing. Some of it's for soybeans. The demand for soybeans continues to go up throughout the world. And what she found was just in the last few decades, the climate in some parts of the Amazon basin, as the forest was removed, has become warmer and drier. And in some locations, the annual precipitation has decreased as much as 50%. And that was the largest. I've never seen anything. I thought there might be a mistake, but we have some replication, and it's real. So again, an example. Thank you for bringing that up. Though another example of this land use, it is a big issue. And so most of the theory behind this for those tropical rainforest areas suggests that they will become warmer and drier. It's not clear. There were some winters. Areas up near the foothills in the Andes, they had increases in precipitation, or have seen over the last few decades. So not everybody got drier. Some areas got wetter. But the problem is when we have to change, or our climate changes, we have to shoot at a moving target. But this is a big deal, and as I showed for the Midwest, there are examples of this everywhere. But the rainforest is a big one, and it's also some of the largest sinks for water that we have on the planet. So it's not good to lose, in general, to be losing those.
Next question.
Yes, ma'am.
My family has owned the same piece of property on Lake Huron for 50 years. And so we watched the low and the high and no low. And that last low, they said was going to keep going even lower. And you say that prediction has changed. And I'm wondering, was it just more information, better modeling, or?
The question regards the recent behavior of lake levels in the Great Lakes, and for somebody who has property on Lake Huron and has seen major changes in the past, including recent one of the lowest levels as recently as the winter of 2013, 2014, and that's a hint as to where I'm going with this. That was followed by the largest increase in history on the Great Lakes, the Corps of Engineers record, and it was followed by that horrible cold winter where Huron, Michigan, all the Great Lakes were covered by ice and it reduced the amount of evaporation. We also had above normal precipitation at the same time, and so we had a jump from one of the lowest levels on record, and I think for Michigan, or for Superior, it might have set a record that year. It was close. We went up to, and it was up in the top 10. It was way up, so a huge, huge change. And my comment to that would be, again, the variability. The variability is increasing, and I had stories, people that were dredging harbors at $10,000 per foot in marinas, and people were being forced to pay all this money because there wasn't enough water, were suddenly faced with flood control within 12 months. That has not happened that frequently in the past, and I think that's the real challenge here. But most of the studies that we have, the last thought here, most of these studies, again, suggest that there's some kind of a balance. So long term, we won't see large shifts one way or the other, like we're going to lose the water or have it all evaporate. But the problem is with how fast it fluctuates or how much it fluctuates. I think that's the key issue, and that we don't, much more research is needed. Yes, sir.
We've heard, thank you very much. We've heard about El Nino and La Nina and the influence that they supposedly have on our weather patterns here. Can you explain how this works? Is it warming from the Earth's core?
Right. Question regarded what's called collectively the El Nino Southern Oscillation, or ENSO. And there are two pieces of ENSO, and then one is El Nino, which I think we've heard for some time, and the other is La Nina. The Spanish nicknames are given because of the discovery of this. It's the largest combined atmospheric oceanic phenomenon on Earth. And the initial observations of this took place on the west coast of South America centuries ago and have occurred ever since. And so it's a periodic fluctuation of both atmospheric patterns and oceanic patterns that change from normal. So we're dealing with large areas of the equatorial Pacific where we have trade winds, and then of course the mid-latitude, the westerlies on both sides of those. And the issue ultimately is, and it's not completely understood, it's been known, some of what I talked about with the forecast models, really since the middle of last century, people started to put the two things together, but it's definitely geographically the largest. It covers thousands and thousands and thousands of square miles in the equatorial Pacific. And how many people have heard of El Nino mentioned in our forecast? I think the original question. What does it have to do with us? It's 10,000 miles away. The answer is that we're dealing with what happens in these phases. El Nino, we see the presence of unusually warm waters in the central and eastern equatorial Pacific when there's typically colder, and vice versa. For La Nina, the nickname La Nina, we see cold ocean surface temperatures. And so what you're dealing with is large changes and fluctuations of the energy balance. Remember back to where we started with, and it's a big deal because ultimately these huge, the Pacific's the largest ocean basin on the planet, and the way that heat is redistributed towards the poles, a lot of it has to do with the jet stream, and it turns out that those El Nino and La Nina events, they interact with the mid-latitudes. And that, of course, that's the primary control on our weather in the mid-latitudes. And so typically, there was an El Nino event. It's actually officially, it's a weak one right now, and it started last fall. And we typically, in El Nino winters, so when there's these conditions are warm water in the eastern Pacific, go on during the northern hemisphere winter, we typically see, not always, but typically see milder and drier than normal winters. And that's what our forecast was. If you looked at the long-range forecast back late last fall and even into the winter, well, it worked a little bit in December and up into the first week in January, but not so much over the last. There's other issues there. And typically, the stronger that these events are, the more likely we are to see. With La Nina, we typically see some of the opposite. We typically see above normal snowfall during La Nina winters. And it's thought, again, what do these things have to do with the global picture? And it's this redistribution of heat from the low latitudes towards the high latitudes. There's some speculation that given these projections of a warmer world, and it's getting warmer now, we might see more El Nino events in the future, but it isn't clear. The oceans are warming up too. Of course, it takes a lot more energy to heat up the water than it does the air. So that really isn't clear, but they do, in terms of our looking at the variability and the variance of our climate, the El Nino Southern Oscillation, El Nino and La Nina, that's the number one signal that shows up, at least in especially tropical areas of the world, but also in mid-latitude areas as well. So that's a good question, but much less, for the future, much less is known about how that might change, but it's certainly an issue.
Thank you.
Yes, sir.
Just in terms of negative impact, as the planet warms up and things start melting, are we anticipating the loss of coastal land mass as the oceans come up? And also as the water temperature in the oceans rise, a dramatic impact on ocean life.
Question was, as the globe warms, the atmosphere and the oceans as well, some of the potential impacts with this, certainly rising sea level, as well as changes in natural ecology, natural wildlife and plant life. This is happening, unfortunately, and there are a number of examples of this. I'll just throw out a couple. Sea level has risen by about 8 inches in English units here over the last century. That doesn't sound like a lot, but the issue is that ultimately if you live along the coastline, that it doesn't take much of a vertical increase for that water to be moved inland. And the areas that are affected by severe storms and so forth, there's, again, an exponential increase. There are, unfortunately now, there are examples. There's a village in Alaska which is having to be relocated because it's literally falling into the ocean. The city of Miami is spending a minimum of $20 million per year for pumps. And that one, it's just like the little boy in the dike. That's a short-term problem. How do you fight the oceans? There's a great deal of evidence collectively, and again, the economists that spent a great deal of time on this, they identified, there's two things, if you look at climate change, what are the two biggest economic issues? And it's hard to think about it. Everything's not money. That's the way they think. But economically, sea level rise is at the top of the list. The other one that's arguably there is human migration and the political problems that result from human migration. But the sea level rise is a real problem to try. You can't prevent it. And 60%, I think, of the world's population lives within 10 kilometers or so of oceans. One other part, that in terms of wildlife, we're seeing bleaching of corals in places like the Great Barrier Reef, also in the Central American tropical systems as the ocean temperature increases and also the acidity of the ocean increases because of both those things are happening, and long term the prognosis is not good. These systems have evolved over a long period of time with relatively stable conditions, and of course we're not stable now. So the sea level increase is a big problem. We're lucky here, relatively fortunate in Michigan. We can, unless we have property, but this is something, and as I showed the house there, it's not a matter really for many of these places of if, it's when. And so one question that many are grappling with right now is insurance. Yes, it's relatively easy to buy property insurance or storm insurance or weather-related insurance, but ultimately that insurance has to reflect the true risk, and the risk, unfortunately, is probably increasing in many areas. So it's a big long-term problem, and I sat next to a very nice young woman on an aircraft. It was a trip to Europe, and you're stuck there for 8 hours, and so you try to make the best of it. But she was an attorney from Miami, and she quite successful attorney. And finally, after I'd been talking to her for a while, I got up and I said, "I'm just curious, but how much does it cost for hurricane insurance?" She lived literally in South Beach in Miami, beautiful condo right across the street from the ocean. And I just said, "If you don't mind, how much does that cost?" And she goes, "I don't have insurance." And I said, "You're kidding." She goes, "No, I can't afford it." And she said, I'll bet of the 16 people in my condo, I'll bet nobody. Because, and that has always stuck with, that was a couple years ago, but I think it says a great deal and about the risk. Again, it's a beautiful place to live, but there is that issue, and the frequency of those events probably, unfortunately, is increasing.
Thank Dr. Andresen for his presentation. I'm sure he'll be glad to stay around and answer a few more questions.
Sure.
Thank you, Dr. Andresen.
Thanks very much.